There might be a graph or two, but
Okay, if there is, just let me know and we'll get through that step where you send me a picture of that graph.
all right, great. So, okay. So I need some help on the domain of logs.
Okay?
So the first one is, I think it's x equals log base 5 of 7.
So using the change of base, now do you understand the change of base formula here?
Yes.
And it's noteworthy that I can use any base I want. It's the same thing. All of these ratios are the same, which is not always obvious. You see what I'm saying?
Yeah.
Okay. So they're not asking for the domain of x because the domain of x is one value. It's a number.
Right.
Let's talk about domain for a bit. If I said y equals the log of x, now you can talk about domain. What's the domain of x? Or excuse me, what's the domain of this function?
Negative infinity to infinity.
No, you cannot take the log of negative numbers.
Okay.
You cannot even take the log of 0. So the domain is from 0 to infinity, but 0 with a parentheses, not a bracket.
Right.
Different than if I said, what's the domain of this function?
Up 0 to infinity.
Ah, but that's with a bracket.
Right.
Because it's okay if x is 0. I can take the square root of 0. I cannot take the square root of any negative numbers, and I cannot take the log of negative numbers. But log functions are even more restrictive. You cannot even take the log of 0.
Okay.
Why is that? Because, remember, we always start with this when we're talking about logs. And for me to take the log of 0 would mean I would somehow have to be able to make y equals 0. Well, you can't do it. No matter what value you make x, there's no way y is ever 0 or negative. In other words, if I said y equals 1 to the minus 1,000th, that's not 0. That's 1 over 1,000, but it's not 0. There is no value I can make x that makes y 0. And since
Okay.
this is where all logs originate, from that starting point, it's also, there's no value of x that makes y negative. I cannot make y negative or 0 as long as b is greater than 0, and that's also part of the premise, is that b has to be greater than 0, but as long as b is greater than 0, then y is always going to be a positive number. And the fact that y is always a positive number means that when you talk about it logarithmically, there's no way that can be, or I have to make x be a positive number.
Okay.
All right.
If the base is greater than 0, but the log there's a negative 1 in front of the log, or a negative number, can y equal a negative number?
So you're saying
Yeah.
Let's look at the log curve. For a moment, let's take away that negative sign. Here's what the log curve looks like. This is x, this is y. This point right here is the same regardless of what base we're using. It's 1, 0. If we take the log of 1 or higher, we get a positive number. If we take the log of numbers between 0 and 1, we get a negative number. I can actually, the range of this function is negative infinity to infinity, all real numbers. Think about that for a second. So what's the log of 1/2 going to be, positive or negative?
Negative.
Okay. And if I took the log of 0.00001, what's it going to be?
Negative.
Negative a lot, right?
Right.
In other words, it's going to approach negative infinity. But if I took the log of 1.00001, it's going to be positive. So that's a good thing to remember. I cannot take the log of anything but positive numbers, but y can be anything from negative infinity to infinity. In other words, the domain is restricted, but the range is not.
Okay.
So the last problem you gave me didn't make much sense. What else you got? In other words, to talk about domain and range, you really need two variables. Well, not quite, I suppose. If I gave you that, the vertical line, 2, what's the domain of that?
2 to 2.
What's the domain?
Would it be 2 to 2?
Yes.
Or is
What's the range?
negative infinity to infinity?
Okay. So you can talk about the range even if it's, or the domain and range even if there's only one variable in the function. But most of your functions are going to have two variables.
Right.
Actually, the one you gave me, what was it? It was x equal what?
It was x equals log base 5 of 7.
Well, that's a number. Which means I don't know what number it is, but it's a vertical line. So the domain is log base 5 of 7, and the range is negative infinity to infinity.
Okay.
Always remember that when you're looking at a log expression without variables, if it's all numbers, then it's just a number. I can get that from my calculator. It's the log of 7 divided by the log of 5 using the change of base. But that's just a number, which means it's a vertical line. If x equals a number, it's a vertical line. What else? Nothing like last night? Man, you gave me some problems last night that I have not seen in 8 years.
Yeah, last night's homework was weird. This one...
But it was very clever. I liked it. It was very, very clever. It was something that you had to think out of the box a little bit.
Yes. Alright, so these are just solving for x. Log base 5 of 2x plus 3 equals log base 5 of 3.
Okay, what am I going to do to that?
Sorry, hold on one second. Uh, should I subtract log base 5 of 3 to the other side and
Well,
then
you
make it?
could do that, but that would make the problem much tougher. There's another principle at play here, and that is if I have the log base anything of a quantity and it's equal to the log base the same anything, a different quantity, then I can set that equal to that.
Right, the common base.
X has to be 0. Now,
Okay.
the question is, you always have to check your domain. It's very, very easy to come up with a solution to a log equation that violates the domain. In this
Right.
case, x equals 0 is just fine, because that means I'm taking the log of 3. But there are lots of cases where you end up with a quadratic that you have to solve, and you have a positive and a negative solution, and one of them usually violates your domain.
So it's extraneous?
Well, with log equations, always check to see whether your solution violates the domain. In this case, it does not. In other words, when I plug in 0 for x, I get the log of 3. Well, I can certainly take the log of 3.
Right.
Sometimes, if I had to come up with a solution x equals 0 or x equals minus 2, well, x can't be equal to minus 2. Because if x was equal to minus 2, I'd be taking the log of a negative number. You can't do that. So you would automatically say that solution is extraneous.
Okay.
But you always have to go back to the original equation, not an adjusted equation. And I can't stress that hard enough. Go ahead and give me more problems. I bet we run into one that's like that.
Okay. So same direction, just solve for x. Log base 2 of x plus 1 minus log base 4 of x equals 1.
Hey, again with the different bases. Well, gosh, that has to equal 1. Well, let's just, you know what, I don't really know a way to solve this, but I know a way to play at it.
Okay.
What's happened if x equals 1? What's the log base 2 of 2?
Just 1.
Okay. What's the log of 1? Base 4. The log of 1 is always 0 regardless of the base. In other words, the log base 17 of 1 is 0. Why? Because 17 to the 0th power is equal to 1. So in this particular problem, I can tell that if x equals 1, then I got 1 minus 0, and that does equal to 1.
Okay.
And there's not going to be any other solutions because I cannot let x equal 0. That would violate the domain. You see why that would violate the domain?
Yeah, because of log base 4.
You cannot take the log of 0. Yeah. I could try some x's that are higher. Now let's try an x of 4. Let's see what happens when x equals 4. So first of all, I have log base 2 of 5. I have no idea what that is, but it's not a whole number. But what's the log base 4 of 4 equal to?
1?
0. Sorry, 1. You're absolutely correct. 1. So I end up with log base 2 of 5 minus 1. Could that possibly be equal to 1? Well, it can only be equal to 1 if that was equal to 2. And that's not equal to 2. Log base 4, or log base 2 of 4 is equal to 2. But log base 2 of 5 is more than 2. So that's not a true statement. That means that's not true. That's got to be our only solution. Now, I came up with it a bit oddly. In other words, I kind of guessed at certain numbers and plugged them in to see whether they worked. And one worked really good. I know it's going to be a whole number. I know it's not going to be a fractional number. So my only choices were really 0, 1, 2, 3, and 4. And 1 works. None of the others do. So 1 is the solution.
Okay.
Not sure how to actually prove it. Boy, your teacher loves these different bases. I never get different bases from anybody else. And I work with a lot of Highlands Ranch students. So I'm surprised, Rock Canyon, you must have a unique teacher that's teaching logs. Because I've had a lot of Rock Canyon students with logs, and I don't get problems like this. What else?
Another condensing logs problem.
Okay.
Log of x plus log of 9 plus log of x plus 1 minus log of 3 minus 2 log of x.
All right. What's the first step of condensing?
Turning the addition into multiplication.
Well, I would say let's work from rule 3 back to rule 1.
Make the 2 an exponent on the x?
Yeah, let's do that first. And then we'll work back from there. Okay, so if I'm going to make this a single log, then everything that's being added needs to be in the numerator. Everything that's being subtracted needs to be in the denominator. So what goes in the numerator?
X, log, do you want me to separate the logs or just...
No, just read the terms.
Okay, x times 9 times x plus 1.
Divided by?
3 divided by x squared.
In other words, that's the way you do it. You can take both of these things that are being subtracted and put them both in the denominator as multipliers of one another.
They wouldn't be divided?
No. In other words, both of these are divisors because they're both being subtracted. But they end up multiplying one another in the denominator. Okay? Now, there's some simplification we can do here.
Right.
This becomes, let's see, x squared plus x, so that becomes 9x squared plus 9x divided by 3x squared. How can I simplify that?
You can take out 9x from the top.
Well, what can I take out from top and bottom?
Isn't the top a binomial, so you can't simplify?
You can definitely take out 9x from the top, but I want to be able to divide it by the bottom also. In other words, if I factor out a 3x from the top, notice that it works a little bit better, I think. And I'm dividing that by 3x squared, so I can cancel that 3x with all but that. So now my final answer looks like 3x plus 3 over x.
Okay.
Now, whether you want to factor out the 3 from the numerator or not, I don't think that's important, whether you do or not.
Right.
The thing is to simplify it, and I've simplified it as much as I can simplify it. I could factor this out so that it's 3 times x plus 1 all over x, but that's not really a simplification. That's just factored.
Right.
The only time you absolutely have to factor is if you can simplify it. In other words, if I can cancel something out. In other words, starting from that step, I can definitely simplify it if I take a 3x out of top and bottom.
Okay.
But after that, it's just a question of whether I want to show that as factored or not. And that's not really simplification. There's a difference between simplification and factoring.
Right.
All right.
Okay, so I have another solve for x.
Okay.
7 to the power of x minus 4 equals 3 to the power of 2x minus 1.
All right. This is an exponential equation. There's no way to solve this algebraically because it's not an algebraic equation.
Right.
When you have an exponential equation, 99% of the time, the solution comes from taking the log of both sides. And you can take multiple logs. I could take common log, I could take natural log, I could even take log base 7 or log base 3. I'm just going to tell you that the one you always are going to want to use is common. Excuse me, natural log.
Okay.
That's the language of calculus, is natural log, not common log. In other words, as you go on in your math career, everything's going to be in natural log. So might as well get used to it now and use it whenever you have to take the log of both sides. Now, the advantage of taking the log of both sides is I now turn it into an algebraic expression because I can take that exponent and put it on the algebra line. See what I'm doing?
Yeah.
Well, now I have an algebra equation. Natural log of 7 is just a number, so is natural log of 3. So I can absolutely solve that. It's a little, we should go through it because it's a little different than solving regular equations. First thing I have to do is realize that that's a number, and that's a number. Well, if I had numbers there, what would I do? I would distribute, right?
No.
And if that natural log of 7 was a 3, I would multiply it by that. So that's what you want to do. I got natural log of 7 times x minus 4 natural log of 7 equals 2x times natural log of 3 minus natural log of 3. You with me?
Yeah.
How do I solve for x?
Get the x's on one side.
Okay, let me take the x's to the right, and I'm going to take everything else to the left. So I got 2x natural log of 3 minus x natural log of 7 equals natural log of 3 minus 4 natural log of 7. With me?
Yeah.
Now what can I do to the right? I'm trying to solve for x.
You can take out an x.
Factor an x out. When I factor an x out, I'm left with this. Over on the right, I still have natural log of 3 minus 4 natural log of 7. There's only one thing that's not a number in this equation, and that's x. So if I divide both sides by that, I'm going to solve for x. I get x equals natural log of 3 minus 4 natural log of 7 divided by this number over here, which is 2 natural log of 3 minus natural log of 7. Now,
Okay, and
can we simplify that in? I don't think so. In other words, I could call this denominator natural log of 9. You see why? That's the natural log of 9?
yeah,
Because it's the natural log of 3 squared.
right.
And I could call this the natural log of 7 to the 4th power, which is the natural log of 49 squared, whatever that number is. But I don't think I can simplify it. I can't do anything with this natural log of 3 and that natural log of 3 and this natural log of 7 and that natural log of 7. I really can't simplify it. It's kind of like having, I probably can, I just don't know how. I don't think, there may be a way to simplify that. I'm not sure what it is. I was going to say it's kind of like having x over x squared. Well, I actually can simplify that, right?
Right.
But when you're dealing with logs, maybe not. I don't see how I can simplify this. There may be a way to do it, but I don't know what it would be. To me, that would be the answer. Do you have answers on these? I forgot.
Not these questions, no. But I think that's the right answer because she's
I would think that you would not lose points on that.
right.
There might be a way to simplify this. I don't know. We could probably not. It would be kind of like asking you to simplify x minus 1 all over x squared plus 1. I can't
Right.
simplify that. There's no way to simplify that. So I don't think there's a way to simplify this expression either.
Okay.
But you can certainly get that number out of your calculator. And if you prefer, oh, okay, no, there is a little bit of, no, yes, there is a little bit of a way to simplify it. Let's talk about that. Almost omitted this. I'm subtracting logs in the top.
Oh, right.
Well, if I put the 4 up there, now I can write the numerator as a single expression, a log of 3 divided by 7 to the 4th. That's my numerator. And my denominator is the natural log of 9 divided by 7. So it's the natural log of 9/7.
Okay.
That incidentally is going to be a negative number because it's 0 to 1. And that will be a positive number because it's greater than 1. So I can't really simplify it anymore. But at least I know more about it. I know it's going to be a negative answer.
Okay.
All right. William, let's wrap it up there.
All right.
And I will talk to you tomorrow. You have a session at 6.
6. Yeah.
I will talk to you then.
Great. Thank you very much.
All right. Bye-bye.